This is Bob Keane live, and I just wanted to let you know that I'll be monitoring the chat box if anybody has any questions throughout the presentation. So go ahead and do it.
Good morning, everyone. I would like to thank the CMP committee for including me on the agenda, and I'd like to thank the organizers for asking me to give this talk. And let me say that I'm incredibly proud to be both before, right after Ann Carlson and right before Mark Parisian. This is a dream of a lifetime, and thank you for putting me right here. This is great. The subject that I'm going to talk about today is interactions and the interactions that occur in the landscape today because of climate change. In 2020, Rachel Lohman, myself, and Lisa Holsinger wrote a paper on how important interactions are and how important it is that we include these interactions in our analysis of climate change effects. And we specifically talked about several kind of interactions that happen. So today, the talk is mostly about the effect of climate change on forest vegetation and wildland fire. And I'm going to show you the importance of the interactions for this, for predicting climate change. Now let's talk about those interactions. You know, climate doesn't just affect one particular aspect of the ecosystem alone. And it's really bad if we want to study the effects of climate that we concentrate it on looking at only one part of the ecosystem, such as wildland fire or whatever. What really happens is climate influences one ecosystem part or component that then influences another component that influences another, and all these interactions serve to create a specific climate effect. So in the crown of the continent, what we have is that climate acts on vegetation, fire, fuels, and so on. And the change of vegetation will influence the fuels, and the fuels will influence both the ignition timing and pattern of the fire and also the fire behavior. The change in fuels and also the change in vegetation will also influence weather through evapotranspiration or whatever, and that could feed back to the macroclimate. So all these interactions are what we have to account for if we want to accurately predict climate change. And of course, humans are really important in this. And once we throw in the human factor, humans can modify or proactively change various parts of the ecosystem to both mitigate and exacerbate climate change impacts. So in this talk, what I'd like to do is introduce our model, FireBGC, and the second version of that, V2, which is the model that we use to simulate ecosystem response. It is one of these mechanistic models that includes interactions. And what I'm going to do is show you just the output from FireBGC. I'm first going to talk about it, then I'm going to show you the output. And in this output, I'm going to show you how we use FireBGC to compare across scenarios, how we use FireBGC to do multiple scenarios and then compare them to HRV, which is historical range of variation. And then we're going to do some threshold analysis where we ramped up the climate in FireBGC and looked at if we could detect a tipping point or some place where there's a threshold that we can say, oh yeah, things are starting to tip off the table and we're moving to a new ecosystem or a new state. And last, I'm going to offer some conclusions about just exactly what this means to the crown of the continent. So now let's talk about the FireBGC model. Again, as I mentioned, it's a mechanistic model, which means it models the most basic physical and chemical processes that we can do, and these basic chemical processes are not dependent on how vegetation changes or how climate changes, because they were developed across a wide range of climate and vegetation and so on. It includes both a fire ignition and spread model. It includes several bugs. It has white pine blister rust. It has mountain pine beetles and so on. And we simulate ecological processes at 5 scales: at the tree scale, at the species scale, at the stand scale, site, and landscape scale. For instance, fire spread and behavior is calculated at the landscape scale, whereas photosynthesis, respiration, and evapotranspiration is calculated at the stand scale. Clone crops are calculate at the tree scale. This allows multiple species, multiple age stand dynamics to be included in the model over large areas. And because each one of these ecosystem processes are simulated at their own inherent scales, we're able to get these cross-scale interactions that we need to actually estimate climate change response. So that in a nutshell is FireBGC. Okay, these are the landscapes that we used to apply FireBGC to investigate climate change. There are only 3 that I'll present in this talk: the Crown, the East Fork of the Bitterroot, and the Yellowstone. But note that over 20 landscapes have been implemented in the FireBGC model, and including one in Alaska. So we've got results from many more. But right now, I'm just going to show you results from just the Crown landscape. We use this simulation design to generate the output that I'm going to show later in this talk. The climate factors, there are only 2. The historical climate, which is the instrumented weather that were collected for over 100 years for all 3 of the landscapes, and an A2 or an RCP 8.5 scenario, which is hot and dry, which is around 6 degrees warmer and 7% less precip. Some of them do have a B2 climate or an RCP 4.5, which is warm moist, which is a little more than 2 degrees warmer and 10% more precip. But basically we have the hot, dry, and the historical is what we're going to contrast mostly. We simulate 3 major fire management scenarios where there's no fire suppression, which is, of course, not suppressing any fires, which is the historical fire regime. Then we have a wildland fire use scenario where it's around 50% suppression. And then we have full fire suppression, which is 96%. 96% of the fires are suppressed, 4% are allowed to burn. These are the 4 that the fire suppression machine could not get at, and so these are the ones that are going to burn the landscape. Some have fuel treatments that we put on. There's 4. There's a no treatment where we didn't do any fuel treatments, and then there's a business as usual where we treat less than 3% a year. A fully funded is less than 10% a year, and then the no holes barred where we treat everything and try to put the whole landscape into something that's not into a fuel treatment. You can see all the outputs variables that we use. We're going to talk mainly about total basal area, but we're also going to talk about proportion of the landscape that is in fire adapted species and so on. Each one of these were simulated with 10 replicates of anywhere from 20 to 500 year simulations, and we generated output for every 25 years. So there is our simulation design. Now we're going to go into the scenario comparison, which is the first part. So we're going to compare multiple scenarios and see what we found as far as climate change is concerned. Here is one of the first results that we found, which I think is pretty profound for the crown of the continent. Here you can see the A at the bottom means the A2 climate, and NF means no fire suppression. So we have A2 climate. Look at all the number of fires per year that we get, and with no fire suppression, all these fires are allowed to burn. Here's a B2 climate, which is the warm, moist one. C is current, or the historical climate, and then we have the WF is a wildland fire use scenario, and then the AFS is the A2 climate with full fire suppression. I want you to notice the 2 arrows. So this is the A2 climate on the no fires, and the A2 climate on the fire suppression. You can see that there is significantly less fires when we suppress fires, but what we found is the average area burned is about the same in the future under climate change. Even though we are putting all this money into full fire suppression, the suppression machine, the 4%, burned just as much acreage as if we just left all the fires go. And this is because, of course, is that as fires burn, they create a fuel break for the future fires. And this self-organized behavior of a fire regime is why we have just as much land being burned when we're putting out all the fires as opposed to if we let them all burn. So here, what are the interactions? Well, it's all about the spatial interactions of burn history. Burn history really influences what's going to happen in the future. Incredibly important if you look at the statistical studies that show wildland fire is going to increase in the future. Don't forget, they just use climate. They did not use what's going to happen to the fuel bed. So this is an important finding from these mechanistic simulation models. Here's another one that I threw in, it's another one of our first things what we found, and this is the cover of western white pine. So the top graph is western white pine with no fire suppression, and you can see how many hectares, what happens if we allow western white pine and allow all fires to burn. What happens is that it takes around 50 to 100 years for western white pine to overcome and become resistant to the blister rust. And then after that, if western white pine is found on the landscape, it becomes very dominant. And these are stands where western white pine is dominant. And you can see the red line is the A2 climate. The baseline is the historical climate. And you can see that western white pine actually does better in the future conditions. And this is because of course, the fires that occur out there. You can see under the wildland fire use scenario of 50% suppression, you can see less amount of western white pine, but essentially the same result. Western white pine does better under future climate and so on. But look at what happens under fire suppression. You get about a third of the western white pine that you get. And of course, if you put out fires, it just dampens out the western white pine, especially in the historical context. Putting out fires ensures that species won't become dominant in the future. So what are the interactions here? It's the genetic interactions of rust resistance plus fire that facilitate the presence and almost dominance of western white pine on the crown of the continental landscape. Here is a scenario comparison. Yellowstone, Jason Clark did this paper for his master's degree at Yale. He had 4 scenarios, historic, and he did, instead of doing a B2, he did an A2 that's low, which is less temperature and less more precip, and an A2 that's average, which is the one that we used, and then a higher A2, I think it was plus 8 degrees Celsius. And you can see that as in climate, we see that forest cover declines. And look at it if we look at the forest cover row and look at the bottom, what happens is that this forest cover is replaced by grasslands. And then, of course, this forest cover decline is, if we look at the second row, is caused by the increase of wildfire. But lodgepole pine is a fire species. So why is it that lodgepole pine isn't staying on the landscape? The third row shows clearly that lodgepole pine declines over time. It never really blinks out, but it does decline. And this is because the fire becomes so great that fire is able to burn a lodgepole stand before it actually set its serotinous cones. And if that happens, that's a site conversion because there's no seed source for lodgepole pine to actually populate that burned area, the second burned area, because the seeds from the surrounding area are serotinous, so they don't get on the site. So here, what we see is the interactions of serotiny with fire frequency. As fire becomes more frequent, you have more double burned areas, more areas that are burned quickly, and something that removes lodgepole pine because the cones did not mature. Very interesting for Yellowstone, and very interesting results. And another example of why interactions are important. Here is one we did. This is for the Crown and I think the East Fork of the Bitterroot landscape. You can see there's a key to all these to the left. So the climate is in the colors. Historic is green, future is blue. And then we have fire management is the SN at the top, which is no suppression. SL is the wildland fire use scenario, and SH is full suppression. And at the bottom, we see R is for restoration, where any restoration treatments, RN is none. RL is low restoration treatments, only 10 a year, and RH is high, where we restored a lot. And then you can see planting is, we actually planted rust-resistant seedlings in this. And basically what you see is for the Crown and the East Fork of the Bitterroot, that restoration indeed helps whitebark to come back. And especially on the East Fork of the Bitterroot, whitebark pine actually does well in the future. And it does well in the future because of restoration, if you look at the fourth box and whisker plot, you can see that the black line for RNPN, where we plant nothing and we restore nothing, you can see the black line is way below the historic. So if we facilitate restoration and planting in the future, what we get is we keep whitebark pine on the landscape. So here's an example of where doing actual restoration techniques actually help whitebark pine in the future. Now, look at the planting where planting is low and planting is high. You can see no great differences between it. And this is because that the results were generated after 200 years of simulation, and planting occurred during that 200 years. And what we found is that during that 200 years, only a few of the planted seedlings had actually achieved reproductive maturity. And so had we done the simulation for longer, to 500 years, we would have seen great differences in the planting technique. But right now, planting does help. If you don't plant anything, you can see, as far as restoration is concerned, we get about as much in the future as we would have in the past. So here's an example where the humans are the management, and the interaction between humans, rusher interactions, and climate allow the ability of whitebark pine to remain on the landscape in the future in the Crown and the East Fork of the Bitterroot landscape. Now let's take a look at HRV simulations. Here's where we took the model and simulated historical processes using historical climate. You can see the range of variation are shown in the blue box, the HRV. The horizontal line is what we have in the present, and this is for the East Fork of the Bitterroot landscape. The y-axis is the basal area that's out there, an average basal area across all the landscape. Then we simulated an RCP 2.5 climate forecast, where we had no fire suppression, wildland fire use, 50% of the fire suppressed, and full fire suppression, 96% of the fire suppressed. And you can see for this, we compare the HRV with these three to glean out information that we can use to manage in the future. And here we can see one of those cases where climate change actually makes the landscape, if we allow all fires to burn, quite different, almost a third or a lot less basal area than we have during HRV. But if we suppress fires, we actually bring the landscape into HRV. Very interesting response. I'm not saying that we should do that, but I'm saying this is what we can use the model for. This is the interactions that occur. We can also do it and take those 7 variables that I mentioned, do a PCA where we take out the first 2 factors of a PCA, PCA 1 and 2, and we can map these dots are every 25 years, and we can see that there's a clear distinction of clouded dots between the blue, which is historic, and the red. Notice for the 50% and the no fire suppression, there are 2 clouds of red dots, and this is where we try to look at these threshold analysis. Somewhere during the simulation, the landscape, the East Fork of the Bitterroot landscape, went from one to another state, and that is what we call a tipping point. So let's use that and let's look at some stuff. Here we have output from Katie Ireland, who simulated several landscapes in the Yellowstone National Park, and she found something unique. She found that the proportion of whitebark pine that's dominant on the landscape, in other words, how much area or the proportion of the landscape where whitebark pine exists and where it's dominant, actually increased under the Hadley scenario, which is the brown. The historic range of variation is in the green, and then 2 other scenarios, the CESM and the CNRM, CNRM is blue and the CESM is magenta, are here, and you can see that both of them had a decrease in whitebark pine in the future in the RCP 8.5, but the Hadley did not, and the Hadley is the warmest and driest of them all. And this was very odd because she found that that in the Yellowstone landscape, it didn't matter what you did for restoration of whitebark pine, and that's the GYCC management and the climate informed management, is that you still didn't really affect how much whitebark pine was going out there. What we found is that under the Hadley scenario, wildfire really increases a lot. And because whitebark pine has such a long seed dispersal distance, they were whitebark pine that's tended to survive the fire, and nutcrackers disperse these seeds quite far away. And so the landscape was actually, because the fire had eliminated all the other species, the only species that could be there was whitebark pine because of its long dispersal distance. So it was the dominant, and so in the Hadley scenario, we found we had landscapes of whitebark pine seedlings and saplings because there was so much fire. And the only dispersal was with the clutch nutcrackers. So here, what we have is that clutch nutcracker interactions with burn history are what's driving the behavior of this particular landscape. Then Rachel Lohman and Lisa and I went and did this threshold detection where we selected a diagnostic variable. And in this case, you can see at the top, it's area burned. And then we ramped the model up in temperature. This is the x-axis, and we did simulations at 1 degree warmer, at 2 degrees warmer, 3 degrees, and so on up to 6 degrees warmer. And then we adjusted the precip to be at the greatest to be 30% greater, and at the less to be 30% less of what it is today. So we have what we have as a box to see. And you can see in area burned, you can see the colors correspond to how much area is being burned. And of course, as the temperature gets greater, you can see more areas burned. We use this kind of detection to figure out if there are thresholds in there. And of course, the thresholds we can determine by eye. In other words, where we go from the lighter shades to the darker shades, or we can distinguish it by statistical analysis. And I'm going to show you two particular analysis that we've done. The first one is this thing called the Swihart Quality QCC. In other words, the two red lines on these 6 graphs are 3 standard deviations above and below the historical range that we got. And in this case, it's the basal area of the landscape. And on the x-axis, you can see what we did is we ramped up fire suppression. Here, we have fire suppression going from no fire suppression at 0 to 90%, actually 98% fire suppression. And so we use the 2 red lines to tell us when all of a sudden the ecosystem is going out of whack. And you can see, I've got some arrows here that you should take a look at. First of all, you can see for the East Fork of the Bitterroot that it goes out of whack right at about 70%. If you suppress 70% or more fires, you go out of whack in the historical. And then take a look at this. This is the no holes barred fuel treatment. If you try to do fuel treatments on that entire landscape, you get a landscape that never occurred historically. Look at in the future landscape, the RCP 8.5. You can see that it starts outside of historical range of variation, and it goes back in at around 70% suppression, which is what we saw in those Boston whisker plots before. Very odd, but very informative if we want to manage this landscape. So let's look at the crown of the continent. Here you can see the crown of the continent seems to be a lot more resistant to climate change and is more resilient. And you can see it really never goes out. To climate change and fire suppression, is that it really never goes out of historical range of variation at 3 standard deviations, which I believe is a pretty wide envelope of historical conditions. However, the crown is also very resilient and resistant to the future. You can see that if we allow all fires to burn, that we get a landscape that didn't occur historically. But if we suppress even 10 or 20% of the fires, we get into the historical range of variability envelope. Very interesting. The exact opposite occurs with the Yellowstone landscape at the bottom. You can see that hardly anything in the future even becomes close to what happens in historical range of variation. And this was shown by the Jason Clark outputs that we see before. So very interesting stuff is that the crown of the continent landscape is very resilient and resistant. The Yellowstone, however, is about the opposite of resilient and resistant. And there is the check points. Here is the fire rotation. In other words, the fire return, how long it takes to burn the landscape, the area equivalent to the size of the landscape. And you can see that the fire rotation is very high. In other words, not very much land burns with only 1 degree, but as we get warmer and warmer and drier, we can see that there are more and more of a landscape burn. But if you'll notice, across all three of Glacier, Yellowstone, and the Bitterroot, is that doesn't seem to be any rhyme or reason to the pattern that is there. And this is because of the feedbacks between fuel, vegetation composition, and previously burned areas across this self-organized fire regime property. So we didn't really get a great threshold detection for fire rotation. But if we looked at tree mortality, here we can see if we go from the top left to the bottom right. Top left is cool and wet. Bottom right is hot and dry. You can see that tree mortality for Glacier increases as we go there, and there's a clear delineation at 3 degrees, or you can see the diagonal that there's a clear delineation. Tree mortality for the Yellowstone, because of the species, is always high. Lodgepole pine is there. It takes centuries for Douglas fir to get there, and so tree mortalities are going to be always high for Yellowstone. But in the Bitterroot, you can see the exact opposite of what happens in Glacier, is that you have low tree mortality now, and then higher tree mortality it barely gets to high tree mortality. And this is because the tree species that are there are able to withstand fire and survive fire. So we get a completely different signal for the Bitterroot landscape. And the same is true for basal area. You can see there's more basal area when it's cool and warm, and then when it's hot and dry, we get less and less. And this is not because the climate is forcing it that way. It's because more and more trees are burned. And again, take a look at Yellowstone. No rhyme or reason to that. Very interesting results, all because of the. So in closing thoughts, I hope I've convinced you that it is the interactions that drive future landscape responses, and that these interactions scale spatially, temporally, and functionally over time and space, and that each landscape, as we saw, between the Bitterroot, the Yellowstone, and the Crown, it will respond different to management actions and differently to climate change. And with that, I've got 15 seconds for any questions. Thank you very much, and I appreciate the time.
Excellent. Thank you, Bob, and I'm thrilled that you're with us here today to answer questions live. If people have those, you can feel free to either raise your hand or pop them in the chat box. And I'd love to start with Kira Hoffman's question. She says, is there a potential that we will see increases in whitebark pine in the 2017 and 2018 wildfires in northern BC, given the extent of the fire and the severity, and then the potential for seed dispersal?
Okay, so this will only happen if the health of the whitebark pine cone-bearing trees around the fire are good. In other words, if there are very few, most of the trees have died, then we have a problem with seed dispersal, because of course the nutcrackers will become a predator to the seeds rather than a disperser. But if you plant those areas, yes, whitebark pine will probably stay on the landscape, and you'll keep it on the landscape. So evaluate your seed sources around the fires, and if you have significant seed sources, then you may not have to plant. But why not plant anyways? Because then you'll increase rust resistance, and you'll have a whitebark pine cone crop there in maybe 200-300 years.
Oh, that's great. Super helpful. Thank you. And really appreciate you putting all of those paper references in the chat, Bob. I know I was busy copying and pasting those so that I can look them up later. So thank you for that. I'm not seeing anyone else's hands raised, so feel free to jump in if you have a question that you'd like to ask Bob. So I think we still have a couple of moments. So there's one from Vita Wright. So she would like to know if we have a link for this one. There's another HRB Fire BGC V2 paper for ecological resilience. So if anyone has that, that would be incredibly helpful. Others? Well, I guess I have one if no one else has one right now while everyone's thinking of questions. But Bob, I guess I'm wondering, so as climate change continues to accelerate, do you have any thoughts about how it might be best to revisit the assumptions or these models in terms of driving management strategies? So like every 10 years or, you know, what would that temporal component look like for really revisiting the way that all of this is playing out and whether or not these assumptions and models are continuing to, you know, predict reality in a way that makes the management strategies currently on the ground make sense?
Yeah, you know, a model is only as good as the authors that made it. And the problem with modeling is that you know, you can never have the perfect model. You'll never ever get it. But so what's really important is that you understand the underlying assumptions and how that model was created. And for instance, you know, you see the statistical models like FVS, Forest Vegetation Simulator, whatever, and they're mostly empirical, which means that they use historical data to create the regression equations that predict tree growth into the future. And of course, if we have a different climate in the future than we had when that data were collected, then we have a problem with that model. And so it's important that you realize that problem. It's not that the model is wrong. It's just that you have to take and visualize and say, hey, okay, so these data are probably out of date considering the new climate that we're in now. Fire BGC, on the other hand, is wicked complex. It has all these interactions and it models right down to photosynthesis and all that stuff. And the problem there is that when you include all these interactions, you're also including all the error that would have happened, right, as a consequence of those algorithms that got developed. So Fire BGC, while it includes all of the interactions, it doesn't do simulations very accurately. The real value of Fire BGC is to compare across scenarios to understand model behavior. So none of these models will give you what you want in the future. And what does that mean? Is that if I were doing land management in the future, I would never do anything that would schedule treatments into the future. I would take a, you know, adaptive management approach and rethink everything after every 5 or 10 years to see what new models are out there, what they're now predicting, and plan accordingly. I hope that answers your question, Ann.
Oh no, that's really great. And absolutely, it feels like everything that you just talked about highlights the tremendous importance of having monitoring and survey informational data that feeds into adaptive management response along the way. So I think we have time for one more question if anyone has one. Oh, here we go, Mike Munoz. Simulation modeling differentiate between first entry, second entry, and third entry fire events and the effects?
Yeah, so thanks, Mike. This is a good question. That's the beauty of Fire BGC, is that it is able to retain the history of the landscape and keep that landscape composition and structure going in the future, where you probably read some of these papers, like a lot of managers in the Yellowstone complex are taking the Westerling paper of predicting there'll be 6 times more land area burned in the future. Whereas all the mechanistic models found that only 2.6 times burned area is going to occur in the future. And that's because, of course, that the statistical models did not look at stand structure or landscape structure and all this stuff, and could not look at for the first, second, and third entry into it. Whereas the mechanistic models can. Of course, it comes with a great cost. It took to do the simulations for just one of the papers that I mentioned there. It's about 8 months on a Cray, 24/7 to do the simulations for the landscape, such as the crown or whatever. So it's, you know, you have to wait a long time for it, but at least the model is able to get at, you know, if a fire burns first, and then what happens when the second fire burns in there and the third fire and so on. So it's able to account for reburn effects implicitly in the model.
Oh, that's great. Thank you so much. That's super helpful. Well, I think we're going to transition to the next speaker, but thank you so much again, Bob. And,
my pleasure.
Yeah, great.